Good morning. So we are ready to take on that last portion of chapter 37. On the previous class we were able to do the first half of the chapter, and now we are ready to take a look at these later topics. So the topics that we're going to be looking at here are, we are going to start off looking at the Compton effect, and then later on we will take a look at the Bohr model for the atom. So let's go ahead and get started here. Arthur Compton did experiments in which beams of X-rays, beams of high energy photons, were scattered off thin layers of materials. So if you take high energy photons and run them through a thin layer, not too many atoms thick, then the X-rays make their way through and you can measure the properties of the X-rays that come out the other side. And what Compton found was that the X-rays coming out had less energy than the X-rays that went in. Now at the time, again, researchers were thinking in terms of wavelengths, and so you could see that the wavelengths of the light coming out, or the energies of the photons coming out, were less. So the basic idea here is that photons transfer energy. Now we already saw this. We saw this with the photoelectric effect. We saw in the photoelectric effect that photons could transfer their energy to an electron, and the electron could separate from whatever material it was attached to. So in this example, with the Compton effect, it looks more like this. The energies that we're using in this case are much, much higher in energy. So here is the incident photon coming in. So this is what's going on before the collision. Now it says that the electron is at rest initially. That's an interesting statement. What does it mean to say, I have a collection of electrons and they're at rest? And the idea here is that when we take a thin layer of a material and we send these photons in, the photons coming in are going to have energies of thousands and thousands of eV. And the energies of the electrons inside the material are, 10 or 20 eV of kinetic energy. And as a result, we can treat the electrons in a material as having really, really low energies. So we kind of ignore the energy of the electrons initially, even though there is energy that's there. So here's a photon coming in, and here's an electron essentially at rest. And what can happen is, if the photon reacts with the electron, if there's an interaction that takes place, then the possibility is that the photon could bounce off in some direction. Now during that process, energy is going to be transferred to the electron. So the electron would experience a force, and the electron is going to bounce off in some other direction. Now the guiding principles, if you think back to Physics 4a, where we looked at similar problems like this, only back in Physics 4a, these were like hockey pucks or something, right? You'd have a hockey puck sitting on the ice, and another one would come in and hit it, and then you would measure the angles that they moved after the collision. And we saw a number of different possibilities back in Physics 4a where there could be a direct impact. Maybe one of the hockey pucks bounces backwards in the collision. So there were a number of different possibilities here. Well, there are going to be different possibilities depending on what angle of collision we have. Now, what this is saying is, kind of a representative piece here is, sure, the angle that the photon comes out at, it could be any angle, but for a particular angle, for the photon, there's going to be a corresponding angle for the electron. We should be able to go in and calculate those. We should be able to determine which angles go together. And we should be able to do this based on energy conservation and momentum conservation. So again, back in Physics 4a, energy and momentum, now they meant something a little different. Back in Physics 4a, the formulas we were using for energy and momentum were limited formulas, and now we've seen special relativity. So we've got to think in terms of special relativity for these collisions, if for no other reason other than one of the particles involved in this collision has no mass, and classical physics doesn't know what to do with particles that have no mass, but special relativity does. So we'll be using special relativity, and we'll be conserving energy, and we'll be conserving momentum. Now, momentum's a vector, so with the diagram we've got here, we can see that the entire collision orientation, we really only need 2 dimensions to keep track of what's going on, but we aren't going to need 2. So we're going to have momentum in the x, conserved, momentum in the y, conserved. There's no need to introduce a third component of momentum, but we will use energy. So that's 3 conservation statements that we can write down. Now, one of the issues I always have with textbooks, and so you guys are learning all of what I think of are either misconceptions in physics or I feel like there are some ways that physics gets presented that are at best misleading and in many cases just wrong. So here's one of them I think is a little risky, and that is always writing photons as these wavy things. Now, we just spent, well, I guess this chapter is really introducing the idea that not just light consisting of photons and those photons having wave properties, but what we're going to find in this chapter also is starting to talk about more and more the wave properties of particles. Electrons, protons, neutrinos, neutrons, they all have wave properties. They're all fundamental particles of nature. Why do we represent light as wavy and electrons as a straight line? So you'll notice in all these diagrams, I've overwritten, see they wrote in the red squiggles, and I covered those over, not very well, with the blue lines. I let you see what was already there. So again, I think we got to start treating these particles more on even footing. That's exactly what this whole Compton effect is all about, is that we can just treat everything as a particle and use special relativity and derive formulas for how these collisions will take place. Now I have to warn you guys, I always use theta for the photon and phi for the electron, and I think our book is using the reverse, so my angles are going to be backwards from the textbook. Sorry about that, but there we go. So here's the photon coming out. Now, see those nice straight lines instead of the squiggles? So here's the photon coming in, nice straight line. See? It's a little circle because it's a particle, and that's what I want to think of it as. And here's a little circle that's an electron. And here's a little circle that's a photon leaving, and here is a little circle that's an electron leaving. And those are the angles, and that's it. So for these reactions, I'm going to characterize this reaction as AB goes to CD. So AB are the particles coming in. Now I'll let A represent my photon coming in, B represent my electron, and then C will represent the photon leaving, and D represents the electron leaving. Now, there's always a question, is the photon leaving the same photon as the one that came in? And particle physics says no. If you are familiar at all with Feynman diagrams, which is something we'll look at this stuff in one of the very last chapters of the course. But in particle physics, we'll see that we do think of the photons as being two different photons, but we do think of the electron as being the same electron. So there are some differences between the photons and the electrons. In any case, we're going to do a bunch of derivations. We're going to look at energy conservation, momentum conservation. Now, the plan is in these derivations, we did this once before. I'm hoping it worked out okay. Anytime I write down m, I really need mc squared. I mean that. That's what it's standing for. And then anytime I write down momentum, it really refers to p times c. So it's kind of shortcut notation, yeah, so that we don't have to be writing factors of c all the time, which is what a lot of these derivations turn into. And then at the end of the derivation, we can put the c's back in if we decide to. Now what that means is when I'm carrying out the derivation, see that m? What's its units? And its units are energy. What about that p? What units do we have on that momentum? And those units are energy too, because it's really standing for Pc. So that's how this works. Now, energy conservation, that's an easy enough place to start from here. We're going to say that the energy of the photon coming in plus the mass of the electron at rest. Now, that's because the electron we're treating as being at rest, doesn't have any kinetic energy, so the energy B, energy of particle B, reduces down to just saying it's just the mass of an electron. Now coming out, the photon comes out with energy, I call that energy C. Now the electron comes out with energy too. And I have to include the mass of this as well as the kinetic energy. I'm just going to call that total energy ED. So a couple things to be aware of. You guys have been through special relativity. You know now that in reactions like this, it's the total energy that's conserved. It's not the kinetic energy that's conserved. So anyway, energy, mass, energy, energy. Now, we can move on to, that's a formula we're going to come back and use. We're moving on to momentum conservation. I'm going to look in the x direction to start with. When I look at a photon coming in, its entire momentum is in the x direction. So I'm going to take the entire momentum of the photon coming in and set that equal to the x component of the photon leaving and the x component of the electron momentum. So those look kind of similar to what we did in physics 4a. And then in the y direction, we start off with no momentum in the y direction, and that says that the y momentum of the photon and electron coming out of the reaction, these two numbers need to match. That's telling me how much y momentum is in the photon coming out. That's telling me the y momentum of the electron. So I hope this is kind of familiar. It should be from physics 4a. So let's do this. There's a number of ways we could proceed. It turns out kind of a traditional way to solve for the Compton effect formulas is to eliminate all of the momentum and energy values of the electron. So we want to remove these from the equation and concentrate on the energy of the photon leaving the reaction. So that's what we're going to solve for. So what I can do is this. I can take these two, see the momentum components for the electron? What I'm going to do is I'm going to take the two components of momentum for the electron, PD cosine phi, PD sine phi, I'm going to square them and add them together. Now, when I square the two components and add them together, I'm going to get the momentum of the electron squared. So what I've been able to do with that is I've eliminated one of my unknowns. One of the unknowns here is phi, that's the electron angle. Now we can come back and solve for that later on, but what we've got right now is we've got like 3 equations and like too many unknowns. We've got a lot of unknowns. We've got to start eliminating some of those. And, you know, for better or worse, we've decided to get rid of phi very first. And so now that's being replaced with momentum of the electron. Let's see what these two things equal. Well, if I take that momentum of the electron, that's equal to PA minus PC cosine theta, and now I need to square that, and then here, the PD sine phi is equal to PC sine theta, I squared that. So it's like, here are the momentum components of the electron squared, and here are all of the rest of the momentum of all the other particles, is what it turns into. Now, when I look at this side, there are things that I can combine. First of all, I'm going to get a PA squared. That's the photon coming in. I'm going to get a PC squared because I have a PC cosine theta squared and a PC sine theta squared. Those are going to add together, right? Sine squared plus cosine gives me 1. And so PA squared plus PC squared. Now, the only thing we haven't included is the cross term right there when we carry out multiplication. So that's going to give me minus 2 PAPC cosine theta. All right, now for the photons, A and C are photons. For the photons, P equals E, right? The photons have no mass, and so that says that PA squared, I could write that as EA squared, and PC squared, I can write that as EC squared. And then also, PA and PC here, those can be written in terms of photon energies. So let's see how we're doing here. We eliminated phi, that's gone. We eliminated PA and PC, those got replaced with energy. The last thing we want to eliminate here is we want to get the momentum of the electron to go away. Now the way we can do that is on the next page. I was thinking we had something there, but we don't. So what I can do is take EA squared plus C squared minus 2 EAEC cosine. This is the momentum squared of the electron. So the electron's momentum can be written in terms of the moment of the electron energy squared minus the mass of the electron squared. Again, that's from special relativity. Let me jump back because it's that last expression in the lower right hand corner, right here actually. Okay, so it's this actually. It's this for the electron, and here's everything else. Now in the next page they're going to flip sides. So they're going to switch to the opposite side. So here's that very same expression, but the P of the PD squared has been replaced by that expression. All right, now ED, the energy of the electron, from here, the energy of the electron can be replaced with EA plus M minus EC. Again, I haven't used my energy conservation formula yet, but now we're going to play that. And what that has done is gotten rid of the ED and replaced it with EA, M, and EC. So now we've gotten rid of everything that we needed to. This formula right here, we've included both components of momentum conservation, we've included energy conservation, and what's left in our formula is the mass of the electron. Now that's a constant we can easily look up. And then there's the energy of the two photons. So the idea is this. Given the mass of the electron and the energy of the photon coming in and the angle, I can now calculate. I want to solve that for energy C. I want to solve it for the energy of the photon coming out. So let's do that. Now, I multiplied this out. There's a lot of stuff in there, right? Because it's 3 terms and it's squared. EA squared, EC squared, there's a plus M squared. Now there's a minus M squared, so I got rid of that. And then there's all these cross terms. 2MEA, 2MEC, 2EAEC. Now, the EA squareds and the EC squared, all the squareds canceled. You know, when I was deriving this equation, I'm thinking, oh no, it's going to be a quadratic, it's going to be a mess. But all the squared terms went away. So that means the formula probably is not going to be too difficult. We'll see. And then what I did was, the stuff that's left is one term right there, EAEC. There's another EAEC term on the other side, and then there are these mass terms. Now, what you can do is you can bring the EAEC terms to the same side. So I now have EA, don't look in those denominators yet. I have EAEC, 1 minus cosine theta equals MEA minus MEC. It's still kind of a mess, but what we do is we divide each of those terms by EAECM. What that does is it cancels the EA and the EC, leaves us with 1 over M. Here we cancel the M and the EA, leaves us 1 over E. So we get this inverse formula. And I boxed this one, that one must be pretty important. So that's it. Using special relativity, we were able to go in and solve for the energy of a photon that has collided with an electron at rest. If the photon going in has this much energy, the photon coming out will have this much energy. It depends on the angle, and it depends on the mass of the electron. Now, we're solving this with the idea of colliding with electrons, but this formula would work fine if it were protons. What if it's protons instead? We could have a bunch of protons and send photons in, particles of light, and bounce them off photons instead. How would I have to change things to solve for a proton? Well, I just put in the mass of a proton instead of the electron. So anyway, that's what the formula looks like. Now, we could also, this is done in terms of energy, and again, that's my preference, but we could also solve for wavelength of the photons. Remember, the wavelengths are hc over E, and that says that anything that is 1 over E could be replaced with wavelength over hc. So that would mean I would get wavelength over hc, wavelength over hc. I could solve for wavelength and move the hc to here. So this is the equivalent formula in terms of wavelength. Now, the book presents this. The book goes through a derivation, not this derivation, but it actually works in terms of wavelength instead. So see what you think. The book uses wavelengths for the photons, kind of a mixture of different quantities. I have tried to stick with just energy and momentum all the way through to see what the formula looks like. Now, a couple things to remember here. The MC squared is going to be 511,000. The HC is going to be 1240 eV nanometers. All right, let's try it out. Here's a problem. It says here that we have X-rays coming in. They're going to be scattered from a very thin slice of something. In this case, it's carbon. And what we're imagining is that predominantly what the X-rays are going to collide with are the electrons. So much more frequently, the X-rays will be interacting with the electrons, not so much with the nucleus. And so that's the idea here, is that the X-rays will scatter off electrons in any material. It says, let's look at 3 different scattering angles, 0 degrees, 90, and 180. So let's try this. Now, here are the 2 formulas that we derived. We derived the energy formula, and then we converted that into wavelengths. Here's what the general picture looked like. Now, in this problem, we are sending in photons with a wavelength of 140 picometers. That's what they gave us in the problem. Now, I quickly converted that into energy and found out that 140 picometers wavelength X-ray would correspond to 8.86 thousand eV. So for the electron, we're going to be starting off with for the electron, we're going to be using its mass of 511 keV. Since this was in thousands of eV, I thought, why not? Let's just do everything in thousands of eV. That'll work. And so at theta equals 0, let's try the formula. If I put in theta is equal to 0 here, that's going to give me 1 minus 1. That drops out. When theta is equal to 0, it says that the energy coming out matches the energy going in. The energy of the photon does not change if the photon is observed to continue traveling directly in the forward direction. So I'm going to say it missed the electron, right? Photon didn't transfer any energy to the electron. Nothing happened. The Compton formula we derived works in the case where the photon missed. And you're thinking, really? Why have a formula for that? Well, it conserved energy and it conserved momentum. It's just that all the energy and momentum remained in the photon. Okay, not so interesting, but it's nice to see that the formula works, even in the case where it misses. Well, let's move on to part B. B says, in this case, photon comes in, but the photon leaving is at 90 degrees. That's quite a shift from the direction where it came in. Now, in this case, in the formula, the cosine theta term drops to 0, and so I just got this to solve for. Now, I think I did this in wavelengths, right? So let's go up to this formula. Plugged everything in. We started with the wavelength of 140, and now we're at a wavelength of 142.4. Now, a longer wavelength for a particle means it has less energy. So when we calculate the energy of these photons, the photon energies now are at 8.71 keV, and we can calculate how much of the energy transferred to the electron. So I can do the starting energy, take the starting energy of the photon and subtract off the final energy of the photon to see how much energy is missing, because whatever energy is missing is now kinetic energy of the electron. And the missing energy is 0.151 keV, or 151 eV. So it's not such a large portion of the energy that was transferred. Now we'll come back and we'll see how that situation could change. The question might be, is it always the case that the X-rays only transfer a little bit of their energy? And it turns out that's not true. There are ways that we can get the X-rays to transfer a much larger portion. Now let's continue with part B. So I drew the picture. Here was the photon coming in. Here's the photon leaving. That's at 90 degrees. I was a little curious. What happens with the electron? What are the numbers on the electron? When we derived these formulas, we focused entirely on the photon coming in and the photon leaving. What about the electron leaving? So what I did was I calculated the momentum of the electron. First of all, I got its y component. Now, if we go back to the previous page, what we can do is see that this photon leaving left with 8.71 keV. That's this photon right here. So whatever momentum that photon has, the electron would have to have an equal amount in the opposite direction. It's momentum conservation in the y direction. So I know what that component's got to be. It's got to be the 8.71. Now, how much momentum does the electron have in the x direction? And the momentum of the electron in the x direction has to match the momentum of the photon. And the photon's momentum is the same as its energy. So the photon momentum coming in is 8.86 keV, and the photon momentum the momentum of the photon leaving, 8.71, because of this 90-degree shift in the direction of the photon. These two numbers are giving me the components of the electron's momentum. So I can combine those. There's Pythagoras' theorem right there. It says that the combined momentum, the magnitude of the momentum, is 12.4 keV. And then I can solve for the energy of the electron. Now it turns out that is not so big. The energy of the electron goes up 511.151, but that 1.1 is familiar. That's the kinetic energy that the electron acquired. And so that extra little piece tacked onto 511 is the kinetic energy from the problem before when we solved it. So that checks out. That's kind of two different ways we calculated that, and we're getting the same number. Now, as far as the angle we can get by taking the y component over the x. Now, these two components of momentum were pretty similar to each other. And so when I take the inverse tangent, I'm getting something very close to 45 degrees, not quite. The x component was a little bit larger. The electron is coming away from the reaction at 44.5 degrees. All right, very good. So definitely B is the hard one. A, the photon missed. In B, this angle of the photon meant that we had to go back and, allowed us to go back and look at the electron properties. We got to ask what happens with the electron in this case. Now the last part of the problem, part C, said what happens if the photon angle is at 180. Now 180 degrees would be the photon comes in, a direct hit, and the photon bounces right back. So it's coming right back in the direction that it came from. That actually should be the way that we would transfer the most energy to the electron. So a direct hit and then the photon bouncing back with the electron going forward. Everything is on the x-axis. There's no y calculations here. Let's try that. So at 180 the cosine theta becomes -1. If I'm doing this in terms of wavelengths, which it looks like I am, then in this case the wavelength went up to 144.9. Okay, so that's the greatest lengthening of the wavelength that we'll see. It corresponds to an energy of 8.56 keV. So that's the lowest possible energy of the photon coming out of the collision is after a direct hit. And in this case, the kinetic energy looks like it's twice as much, right? So the kinetic energy of the electron, instead of being 150 eV, the kinetic energy is 300 eV. And it's still a tiny portion of the photon energy coming in. So we were only able to transfer a small amount. But this is a pretty good problem to look at. So this is keeping track of three particular angles for this Compton effect, for these photon-electron collisions with high-energy photons. Now, I wanted to throw in some other useful energy formulas for the Compton effect. We could start from the energy formula that we calculated and solve for E. So I did that. What I did is I got a common denominator, and then I flipped the whole equation over, and I ended up with this. So I put it in a yellow loop here to emphasize it. So the energy of the photon coming out can be written as a portion of the total energy that the photon came in with. So it's kind of like saying the energy of the photon coming into the reaction is going to end up in one of two places. Either the energy of the photon remains with the photon coming out, or it transfers to the electron. Now we were asking, how could I get as much energy as possible transferring to the electron so that there would be a big drop in the photon energy? And this is one piece of that. So what this is saying is that the photon is going to get that fraction of the initial energy of the photon coming in. So let's see, how would I get that to be a big number, or a small number, I'm sorry. How do we get this to be a small number? What we want to do is make the photon coming in much more energetic. So the photon we sent in had, what was it, 8,000 or 9,000 eV compared with the electron mass. So the electron mass is 511,000, but the E naught that we looked at was only 8 or 9. If we sent a photon in, a really, really high energy photon, there it is, 8.86. If we sent a really high energy photon in that was hundreds of keV, a photon with hundreds of keV would be better able to transfer its energy. So as we go to higher and higher photons, more and more, a larger and larger fraction of the energy transfers to the electron. That's the way it works. We can also go in and calculate a complementary formula. So this much of the energy remains with the photon, this much transfers to kinetic energy of the electron. If I add those two numbers together, you can see that we've accounted for all of the energy coming into the reaction. So, so that's kind of it. This is the Compton effect. Here are formulas that we can work from in terms of more directly looking to see how the energy is going to divide up. The formulas we had before, when you have those 1 over inverse formulas, those are hard to see what's going to happen. If I change one of the numbers, what's going to happen? These I feel like are easier to use a little intuition to see how much of the energy will transfer in each direction. Okay, so useful energy formulas to think in terms of. Now, we've looked at a lot of things that can happen with photons. We introduced this idea of photons as particles, and now we've looked at examples, really everything we've looked at, the thermal radiation, photoelectric effect, Compton effect, where these particles of light, we're seeing what kind of reactions can take place. So in the photoelectric effect, the photon was absorbed, an electron separated from the material. We could also have photons that can't release an electron, but they just get absorbed. We can also have a photon that scatters and loses some of the energy. This is the Compton effect. This was photoelectric. This was boosting an electron within an atom to a different quantum state. We can also get photons that produce, now these are really high energy photons, but they can actually produce particle-antiparticle pairs. So this is called pair production. Here is a high energy photon coming in. Now, the high energy photon interacts with a nucleus, it turns out. The nucleus is unaffected by this, except that the nucleus allows, the nucleus is able to contribute a little bit of momentum. It turns out that a photon by itself, no matter how much energy it has, can't split into an electron, anti-electron. This is an electron, this is an anti-electron, or a positively charged electron. Photon can't do that because there's no way to conserve momentum. So what the nucleus allows for is that there's a little interaction with this nucleus when this reaction occurs, and that allows energy and momentum to be conserved. Now, again, they've represented the photon as kind of this wavy thing. So I circled it this time. I should have put a line through it. I circled it this time and I go, I don't know if we want to keep thinking of these as always having to be a squiggle. Anyway, here's a problem in pair production. Let's take a look at this and see what we've got. Here is this photon coming in. Here is the E plus E minus. Here's a little contribution from the nucleus, which consists of a second photon. So the nucleus actually is able to contribute another photon, which balances out the momentum. So in order to create the electron-anti-electron pair, we need enough energy to create those new particles, because the photon doesn't have any mass. So we're going to need the photon to come in with enough kinetic energy to create the mass of both those particles. Now, two of those are going to be 1022 keV. That's the energy of the photon we're going to need. And I'm going to say that's the most important thing, again, is the energy of the photon. Now, if we convert that into a wavelength, it works out to be 1.21 picometers, where pico is 10 to the minus 12. The 1240 that we've been using here, notice it used to be EV nanometers, but I've switched it into keV picometers. Turns out that there's different combinations of units that we can use for our 1240. This comes from boosting the energy by a factor of 1,000, but shortening the distance by a factor of 1,000. So I can keep using this 1240 shortcut using some different units for that. Okay, a couple things we want to talk about here. The book, talks a little bit about kind of the philosophical ideas behind quantum mechanics, and you guys are not required to write a philosophical essay on quantum mechanics, but they create often, I feel like, especially this particular presentation that I kind of inherited here, that there's kind of a false dichotomy. I don't know if you guys have taken English, English 5, critical thinking. One of the logical fallacies in reasoning, in promoting arguments, is to say it's either got to be this or it's got to be this, when in fact you haven't established that they're two complementary groups. So what they're saying here is that light is a wave. Light has to be either a wave or a particle. Now what that would suggest is that somehow particles and waves are mutually exclusive, but they're two categories that are the only two possible categories we could imagine classification of something into. So I don't think that's that useful. First of all, I really am pushing to not think about light as a wave. I know in common language we always say, here comes the light wave, here comes the light wave, here comes... We could just say, here comes the light, or here come all those photons, but we do tend to attach wave onto every time we talk about light. I think it's a bad habit that we've gotten into. So again, it comes down here, we have to answer this, so let's think about what we mean. What happens here is that the photons are particles. Light consists of these fundamental units. Now it turns out the particles in physics 4c are not the particles from physics 4a. In 4a, a particle was a chunk of something just sitting there. Oh, there's an object, or there's a particle. These particles have more interesting features. These particles don't have to follow one path. They have interference effects that take place. So I always feel like it's more useful to say, yeah, everything consists of these fundamental units. Let's call them particles: electrons, protons, photons. But we're going to spend a lot of this course learning what the properties of these particles are. And they're not as simple as saying they're a little chunk of something sitting there. There's more dynamic stuff going on. So anyway, just thought I would toss that in there. This feels a little better to me, saying that complementarity says that particle aspects of light and their interference effects, they both are part of the package. So let's do this. Let's do some wavelength calculations. This says of a baseball, I guess. I assumed it was a baseball. So example 3710, we've been looking at light and it's, as particles and talking about properties. Well, let's go in and look at the wavelength of a baseball. Now, the fundamental formula we said for calculating wavelengths is h over p. The momentum of an object determines what its wavelength will be. Well, if I got a baseball with mass m, 200 grams, going at 15 meters per second, it's not much of a pitch, right? 15 meters per second. A good major league pitcher should be throwing up 40 meters per second, so it's not much of a fastball. But P equals mv, that's 3 momentum units. That's, 3 Newton seconds of momentum. And I plug those numbers in. So I put in the h, I put in the p for this. I got a wavelength of 2.21 10 to the minus 34 meters. That is a really, really, really tiny wavelength. Now imagine if we had an opening, let's go back to single or double slit interference effects. Let's take a bunch of baseballs and throw them through a slit. The slit will have some kind of a width to it, and see if we get a diffraction effect. Well, what we're going to run into in this example is that the opening is always going to be bigger than the wavelength. The wavelength for these baseballs is 10 to the minus 34 meters. The opening's got to be big enough, I guess, so the baseball can fit through. It's just not going to be practical to set up an experiment where we look at the diffraction effects of large-scale objects, I think. As far as I know, no one's done any experiments like that. Now, there's another question that comes up in any case. If I look at a baseball, the baseball's got a lot of protons and neutrons and electrons in there, and those protons and neutrons and electrons all have their own wave functions and wave properties. How can I create a composite object which still has wave properties to it? So anyway, these are kind of interesting to speculate about. I don't know what the current state of the art is as far as doing experiments. I know people do experiments to try and see if they can see quantum effects, interference effects on large-scale objects. But we're going to leave it at just kind of a curiosity here. Here's something that more similar to what we might run into, and that would be something like this. What's the wavelength of an electron? Let's say the electron goes through, the wavelength is going, here it is. So here's an electron. It's gone through a voltage of 100 volts. Now what that means, because you guys all took physics 4B, is that the kinetic energy it comes out with is going to be 100 eV. So that's the energy, kinetic energy of the electron. Now I've got my quantum formulas right here, so I can solve for a frequency, I can solve for a wavelength, and I thought that 100 eV, it's not going to be that fast, so I went ahead and used classical physics. Now classical physics would say the kinetic energy is 1/2 mv squared, so I can calculate the v as 2k over m to the 1/2. Now I can take this formula, which is from physics 4a, I can add a couple factors of c, and I'm going to claim this is a shortcut. At least at first, I'm sure you guys are going to disagree, but give it a chance, see if this works. If you don't want to try it, it's fine. But try solving this, the physics 4a way, and then throw in these extra factors of c and see what happens. Because what happens with mc squared now in the denominator, I can just take that 511,000 and just plug it in. It's just one number that represents mc squared. And then I can leave my kinetic energies in eV. I don't have to use joules. I don't have to do any units conversion. And so I can plug that in. It says my speed is 0.0198 times c, which converted out into 5.94 10 to the 6 meters per second. It's pretty fast, even at 100 volts. Now, I got the speed. What I'm interested in, even more so, is the wave properties. So an electron traveling at that speed with this much kinetic energy. Now to start with, I've got Planck's constant in these formulas. I want to scale a Planck's constant down into eV. Now we're used to using joules as units in Planck's constant, but what if we use eV instead? That might be a shortcut. I'm going to take that calculated value of of Planck's constant, I'm going to write that in my notes because that could turn out to be really useful. Now, to find the frequency of the electron, I take the total energy and divide through by Planck's constant. Well, the total energy is, I took my 511,000 and added 100 EV onto it. That's the kinetic energy. So that's the total energy divided through by Planck's constant. It says the frequency is 1.23 10 to the 20th per second. What does that even mean? It's an enormous number. And it means that the phase of the electron, if I pick a location in space and ask how rapidly phase is changing, it's going through 1.2 10 to the 20 cycles every second, which again is an enormous number. For wavelength, what we want to do is Planck's constant over p. Now, this I could use instead. I could put a factor of c top and bottom, so that's the one I used. And so the hc on top is my old friend 1240. We've been, or your new friend 1240, that we've been working with. And so I could calculate momentum also. Now I can write that as mv, since the electron's not going all that fast. And again, I added some factors of c and was able to write that in terms of mc squared times v over c, and determine the momentum to be 10,120 eV. So again, I'm going to claim with a little practice, these are faster solution methods than keeping track of all the conversions into joules and then kilograms and converting all the units. Anyway, I ended up with a wavelength of 122 picometers. So there you go. We can calculate. Those formulas are general for every type of particle. They work for photons, they work for electrons, it's a starting point for whatever kind of particle we're looking at. That's what we want to start with. Now here, they're just telling us that the wave nature of matter is important for electrons. The wavelengths here can be pretty short. I think we're due for a break, so let me stop right there. We're kind of in the middle of looking at these wavelength properties, but I think this will be a good place to stop, and then we'll come in and pick this back up.